This information is brought to you by Charles Sturt University.
Hi, this is a short video explaining how to do vector line integrals. So a vector line integral, like the one just here, is when we have an integral along a curve in 2 or maybe even 3D space, where we have either lots of dx, dy's, or equivalently sometimes we might write for short f dot dr, which is really shorthand for this. And so for when you've got two variables, f has two components, p and q, say, and dr has components dx and dy. And so when we write f dot dr, it really just means the same thing. So a vector line integral just has lots of components, dx and dy's. Because this sort of format has a few special results which can be helpful to work things out. So I've got two examples that I want to cover in this little video, and I just want to go through the strategy. So the basic strategy to try to do vector line integrals is, one, you've got to check for a closed curve. Now, if it's closed, then a great way of doing it normally is to use Green's theorem. Now, if it's not closed, we have to do something else. So check for if it's conservative or not. If it is conservative, then the fundamental theorem of line integrals works quite well to work it out. There's a little bit more work, but it works quite well. So I'll explain what that is on the next slide. The third thing, if both of those fail, so if it's not closed, it's not conservative, then sometimes using trickery you can do one of the above two forms, more like Green's, but most of the time you're just going to have to integrate by substitution. What I mean by that last one is we're going to have to parameterize the curve. Once you parameterize the curve, just use the parameterization to work out the answer. So let's show you this strategy in action by doing some examples. So the first example is got a vector line integral, you can tell for the dx dy, and we're going to integrate it around a unit circle clockwise. So clockwise circle. And just want to stress the clockwise here because that makes a big difference. So first let's check, is it a closed curve? And yes, well, yes. Circle's a closed curve, and therefore, so Green's theorem is going to be a great way of doing it. So we don't have to worry about everything else. So with Green's theorem, a few things. We need to know what P and Q are. So they're just the functions in front of the dx and dy. And so what Green's theorem is, under the right conditions, a vector line integral around a closed curve is a double integral of qx minus py. So we just have to work out these conditions. So the partial derivative of q respect to x, well, is partial derivative of y respect to x is nothing. And partial derivative of p respect to y is just going to be x. So it's going to equal to minus x. So at first glance, and this is not actually correct, the line integral around the curve dx plus y dy, by Green's theorem you would think would be the double integral over the enclosed region, which we'll call, say, d for disk, so it'd be the enclosed region, so we'll call it d's the green part. So the doubling over of d of this expression, so minus x dA. So you think that to be the case. Not quite true. So how Green's theorem works, so these two things match up. so long as the orientations match up. So when you're using Green's theorem, any integral or dA really requires that the curve goes around in an anti-clockwise fashion, anti-clockwise. But we have clockwise here, wrong direction. So why? What do we do? Well, if we just change the orientation, all it does is change by a minus sign. So let's do a few things. So a few first notes. Green's theorem just implies the basic equality. And we just got to put a minus sign just to fix up for the fact that it's clockwise. Now if it's anti-clockwise, then not a problem. And again, if a question doesn't state what the orientation is, then just assume that the standard, so the defaulter is to go anti-clockwise. So now we've got that, we're integrating of minus, integration over the disk of, well, it's going to be minus 1, so positive x dA. Now, the simple way of doing this is to go, well, when you're doing a double integral of x over anything, that's the x coordinate of the center of mass times by the, which I'll say mass or area of the region. Now, which is not as helpful, but in this case it is. So if you look back at our disk, the x coordinate of the center of mass would be, well, for a circle it's completely symmetric. The center of mass is going to be right bang in the origin there. So the x coordinate is just going to be 0 times by the area, which we would work out if we wanted to, and that's going to be equal to 0. So quickly you can see the answer is 0. Now, how would you work it in more general terms? Well, you're going to have to parameterize. Now, D is a bit of a circle, and so using polar coordinates is a good idea. So, alternatively, we're going to work out polar coordinates. So x is r cos theta. dA is r dr d theta. R ranges, well, it's a circle, so area from the origin up to the edge of the disk ranges from 0 to 1, and theta, well, it's got to be the full revolution, so 0 to 2 pi, for example. Now, because there's lots of r's and lots of thetas all separate, we can separate the integral, so we can integrate all the theta parts separately. So you can only separate integrals like this if the inside function, so this one here, the integrand, basically is the product of function of all r's, function of all theta. So they've got to be, you can better pull them apart completely, which in this case you can. So we've got r squared dr. So the integral from 0 to 2 pi of cos theta, well, integral of cos theta is sine. We want to do that from, say, 0 to 2 pi. And the integral of r squared is going to be r cubed on 3 from 0 to 1. So plug the 1 and 0 into here, you're going to get 1/3 minus 0. Sub in 2 pi into sine gives you 0. Sub in 0, you get 0. So 0 times 1/3 is just equal to 0. So both the short way and the long way show you that the double integral is 0, and therefore the original line integral, which is clockwise, is also 0. Now, if it was anti-clockwise, minus 0 is also 0, but just want to show what happens there. So that's sort of the first question to do. So just reiterating, if you've got a line integral, vector line integral, check for closed curves. If it's closed, try Green's theorem, and just a little caveat, make sure it's anti-clockwise. If it's not, chuck a minus sign to fix it up. What happens if it's not closed though? Here's another example. Let's do this, almost the same example, but instead of integrating around the full circle, let's just do it half the circle only. Well, it's not closed, so we certainly can't use Green's theorem directly. What else can we do? Well, let's check if it's conservative. The function's conservative. Well, in general, So the function, if we can write down the same function f as being all different components, so it's got the x, y, and y, other two components in this case. So we could think of them as being p and q for short, just give you names for them. So in general, if the curl of f is the zero vector, that's a one way of checking for being conservative. In this special case, when we've got two variables, so just even you've got two components, p and q, so that's what it's 3D. Well, D2D works for 2D2, but in 2D you might as well use the simple formula. You just want to check it. Qx minus py equals 0. That's a simple way of checking for things being conservative. They all just really boil down to make sure that the mixed partial derivatives being equal to each other. That's what it comes down to. Anyway, so that's what we need to check for. So let's check in this case. So in this case, Qx, well, we've done this already, haven't we? So Qx is 0, Py is x, that's equal to minus x. Well, that's not 0. So it's not conservative. So just reading, if it was conservative, then you would work out what the corresponding potential function is. And then once you've got the potential function, then you sub in the endpoints beginning and end, and take the difference, and that bang gives you the answer. So the hard work is finding the potential function in that instance. So if you go back to our strategy, well, it's not closed, it's not conservative, well then we have to fall back, in this particular instance, just to parameterising the curve is that a default option. And you can be tricky and close the curve off and do things like that, but at the end of the day, you have to parameterise at some level. So let's just explore how to do that rather than do anything else. So it's a circle, so we're going to parameterise it. Now, our standard parameterization is x is equal to cos t or theta, let's write down t for short, y equals sine t. Now, that parameterization makes things go anti-clockwise, but you can see my curve here is clockwise, so I've got this little duff up again. So how can I fix it up? The simple way is just saying t goes from, well, instead of being at the top, so the top angle here is at the angle of pi and 2. So instead of starting at pi, so we're going to start at pi and 2 and go down to minus pi and 2. So the easiest way of getting the clockwise idea is just to do the parameters in reverse order, really. And that's the simplest way of doing it. So now we have that, we're going to have to plug everything in. So x and y we know, so that's x, y, and y are all okay. So you have to work out what dx and dy is. So dx is the derivative of x times by dt, which in this case, so derivative of cos is minus sine dt. And similarly, the part dy is the derivative of y with respect to the parameter times d of the parameter, and derivative of sine is cos. And so putting it all together, the integral of xy dx plus y dy. Well, when we integrate, we're going to integrate respect to the parameter t now. So it's going to be from, as I said, from pi on 2 to minus pi on 2. X, y is cos times by sine dx is minus sine dt. That's that part's the dx, plus y, which is sine t, and times by dy, which is over here. So cos t dt. Let's give yourselves enough room to write it all down. Now, you've got to simplify it somehow or other. So I can see a cos t dt is a common factor, so that's what I'm going to do. So I'm going to write down and say minus sine squared t plus sine t outside of cos t dt. Now, this is integral of all these different trig stuff, and so you might know some various methods from Maths 1 or 2 how to do this. In this instance, I can see that I've got a function of sines here. The derivative of sine is cos t, so therefore letting u equal sine t, let's make it s even, let's call it s equals sine t, will do it nicely. So the differential of s is going to be equal to derivative of cos is sine dt. And so the reason why I picked s is sine t, you can see that this part here is going to be the differential. Nicely matches up. So we've got minus sine squared plus sine, integrating with respect to this s variable. What are the limits for s? Well, if x is, so for t, the angle, so to speak, is minus pi and 2, set that into here, sine is minus 1. When t equals pi and 2, sine is equal to 1. So it simplifies down to that integral. To integrate it, integral of minus s squared is minus s cubed on 3. Integral of s is s squared on 2. And we want to plug minus 1 to 1. And again, we've got that reverse order just because it's clockwise rather than anti-clockwise. So plug in minus 1, we get a third plus a half. Minus, sub in 1, you're going to get minus a third plus a half. Now, you may have noticed, because s here is odd function originally, so that term will cancel out. And because the original term is even, we're getting double what we get for the first part. So a third plus a third gives you 2/3, thus being the answer. So just reiterating, if you've got a vector line integral, check if it's closed. If not, check if it's conservative by checking that either one of the two, that qx minus py is 0, or more generally if the curl is 0. If it's not conservative, then you really have to fall back to parameterizing. And the key part of parameterizing, as you can see here, is really just to let dx dy be the derivative times by that d of the parameter, and plug it all in and hope the integral's not too complicated for you. But make sure you do check for the more high-level theorems where possible. So I hope that helps.